Welcome everyone. What we're going to look at in this recording is we're going to look at single phase rectifiers, and I've brought a couple. I have a couple here to show you. Many of you have seen these kind of things. They're all over the place. Everybody uses these. Here we have a this is just an adapter actually for a scanner, and the way this works is the input is 120. 100 to 120 volts AC input, and the output is 13.5 volts DC. So what we have inside of here is actually a single phase bridge rectifier, and also almost for sure there's a transformer that first of all steps the AC down to an appropriate level and then rectifies it to the 13.5 volts. Another very common rectifier circuit. Many of you see, you're going to have these all over the place. These are for your phones, your tablets, things like that. Anything with this 5-volt USB connector. These units, of course, just plug into 120 volts, and there's your 5 volts out. So what we have inside of that is same thing, also just 120 volts in, a little transformer, and then we're taking it and rectifying it to a DC voltage for whatever the device needs for charging or just for power. All right, so we're going to take a look at these. I'm going to show you on the board. We're going to write some details down and take a look at how these circuits work. Okay, we're going to start with the single phase half wave rectifier, and there's just a few facts that I'd like to put down right at the beginning of each of the different types of rectifiers. And so first of all, we're going to start with the single phase rectifier, and this is going to be the half wave. Half wave rectifier. Now the half wave rectifier requires just one diode, and so the second thing I want to do, my second point, is I want to show you the circuit is very simple, and it looks like this. We start with an AC source, just like that. And what we do is we go from the line and we go immediately into a diode. And from that diode, we then place what will be our DC load resistor. And then that load ties back to the neutral. So here we have the diode and the load. And bear in mind, this is a DC load, this is a rectified voltage coming from the AC line. Now, the next thing I want to do is I want to move on, and I want to talk about the waveforms that will appear. So if I take a scope and I place the scope, position 1 would be placing the scope here. Scope right across those 2 points. What I would see would be my line waveform, my supply waveform. And if I took the scope and I placed it here, what I would see is my output or load waveform. Okay, so I'm going to write that down here. Output, and this is really the input or the line. Okay, and we're going to go ahead. I'm going to show you those just next. Okay, so what happens is if you place the scope across the input, we have an AC source there. What we would have is an AC waveform of voltage. It would show up, roughly speaking, like this. Okay, when we'd see our AC waveform on the input. Now, what would happen actually with the load is that the diode, during the first alternation, while it's forward biased, would pass the current, and so our load would see that alternation. And then, as soon as the AC voltage switches, now as it comes this way, the diode is reverse biased and it blocks. And so for the load, what we actually see is this. Just flat line, nothing, no voltage there at all. Okay, so there's the end of the cycle. So what you see here is a full AC waveform on the input, and here, during the same period of time, one full cycle, what you're gonna see here is just one ripple. And then on the other, the negative alternation, you're gonna see absolutely nothing for the load. Now, what we need to talk about is how is this going to work out in terms of how much load voltage there is, okay? And so we're gonna look at something called form factor, and we're gonna go there just next. All right, now with a single phase rectifier, if we were to look at just one alternation, and we know that the peak is 1.414 times the line voltage. So if we take the line voltage here of 120, we know that the peak is pretty close to 170. And the average voltage in a single phase half wave rectifier is just 54 volts. Now, what I want to introduce you to is something called form factor. And form factor is it's really a factor that you could quite handily memorize for each one of the rectifier types. And for this particular one, this form factor is 0.45 times E line. Now the form factor is always some factor times E line, and it gives you the average load voltage. So this equals the DC load voltage or average voltage. Now, I'm going to show you how we arrive at this form factor, but in fact, once you, if you memorize this, it's going to steer you straight every time. But let me just quickly show you how we actually arrive at this value. Imagine this. Imagine that you had a large lobster cooking pot, which would look something like this. And let's say that this is the 100% fill line, 100%. And what I'm going to put on here is another line, which would be, just to compare this to electrical terms, this would be 70.7%. And of course, if this was 100% E peak, this would be E line. And so what we want to look at is we go, how do we really come up with this form factor? So imagine this. Inside of this lobster cooker, we take and we place an ice sculpture of one alternation, okay? Just one alternation. Now remember, in a single phase half wave rectifier, we have an entire cycle that would represent the full width of this, and 100% is the peak. So the peak of the waveform would be right there, and we just have one cycle. So really what we want to find out is if we take and we turn on the heat under this, okay, so we've got a burner here, and we turn the heat on, and we're going to melt that block of ice down. How far is it going to go? Where is it going to actually settle? And so here's what I want to show you. This is quite interesting to look at. I'll do it in a different color for you so that you can see. So once all of this ice melts down, where does it stop? Well, interestingly enough, it would be down right about here, okay? And so you would actually, once melted, it would turn to water, and it would fill the bottom of the pot to that level. Now, let's do a little bit of math on this and see where that brings us. The number for average, if we look at this, the average of one alternation is actually 0.637 of 100%. And when we only have one in here, that means it's going to be 0.637 divided by 2. And so what we're going to find is that's roughly, let me see, 31.85, I believe. Let me double check that. All right, so what we would have there is actually 31.85%. Now let's use the numbers, the voltage numbers that we had here. If 100% is 170 volts, that means that E line would be 120 volts. But if we take 31.85% of 170, that voltage comes up to be 54 volts. And here's where our actual form factor comes from. With the form factor, we simply take 54 and we divide it by 120, and we see that that's a factor of 0.45. So it's the relationship of this 54 volts and the 120 volts of line voltage. So those two represent our form factor. So now just so you see where it comes from. And the form factor is, of course, very handy, especially once we're going to be looking at several different types of rectifiers. So it's very handy to have that point that you can memorize for each one of them. Okay, average voltage is E line times 0.45 for the half wave rectifier. We're going to take a look right now at rectifier values and specifications. So the first point was just the number of diodes. The second point was the circuit diagram, showed you just how that rectifier wired up. The third point was the waveforms and how we arrived at that value of voltage. And so here are the specs, the things that we need to keep track of when we do these rectifiers. Okay, so the first thing, form factor. Okay, we just talked about that. For this one, 0.45. Okay, the second value that we're very concerned with, of course, is what is our E average? And so we really use the form factor and the line voltage to arrive at our load voltage or our average voltage. A very important value in the circuit. The peak inverse voltage of the diodes that is required. So PIV of the diodes. Okay, that's an important factor, a number that we're going to have to look for in these cases. And as soon as we connect one of these up and we have load current flowing through, the diode, of course, is going to be passing that current, and we have to see what is the current of the diode. What is the rating of that diode? We have to be able to pass a certain amount of current in order to expect the diode to be useful throughout its life expectancy. The next point that we need to take a look at, something called ripple frequency. And I will explain that just shortly in the next frame. So we have form factor, average voltage, ripple frequency, diode current, and PIV. Now just two things left. Another thing that we are going to be very interested in is what is the ripple voltage? Ripple voltage. And another name for ripple voltage is peak to peak voltage. And the final point that we need to look at when we're looking at these rectifier circuits is what is the actual load power that is dissipated. Okay, so these are all things that we're going to want to calculate with rectifier circuits. Now, I think that the best way to go at this is that we actually create an example, and then we'll work our way through it, and we'll touch on all of these points before we finish it. Okay, here we have a single phase half wave rectifier example, and you can see just here I've drawn the circuit, 120 volts AC supply, and a diode here, and a 7.5 ohm load resistor. Now, let's work our way through this. Typically what we want to look at is use our form factor, which is 0.45. And so 0.45 times our line voltage of 120 volts is 54 volts DC. 54 volts DC. So that is what we would actually see expressed right here across the load. We put a DC voltmeter, we would see 54 volts right there. Now, how much current would that give us? So we simply take our 54 volts divided by 7.5 ohms, and we see that we have a DC current of 7.2 amps. Now, that 7.2 amps, seeing as there's just one diode here in series, all of that current is going to have to go through the diode. So if we look over here at the current of the diode, it is going to be 7.2 amps. The other thing we could say is it will be the load current times 1. Load current times 1. Now, what else can we look at? We've gone ahead and we got our E average of 54 volts, and we got our 7.2 amps for our diode current. Let's look at our ripple frequency. Now, what does ripple frequency refer to? Now, if you look carefully at this, this is our supply frequency. If I had 60 hertz here, which unless otherwise stated, we will be working with 60 hertz. So if I have a supply frequency of 60 hertz here, every single time that I get one full cycle on my supply side, I get one ripple. And so the ripple frequency in a single phase half wave rectifier is 60 hertz, or the supply frequency times 1. Now, what about the PIV? Well, we know that as this diode conducts current through here, we're going to have 0.7 of a volt drop. The rest of it will be across the load. But when the AC switches and starts to push the other direction, this diode is going to block. How far does it have to block? Well, it has to block essentially this entire distance right here on the negative alternation. And so really, what we would say is we have to block the peak voltage of the supply. Now, another way of looking at that is E line times root 2. Now, root 2 is equal to 1.414. And many of you will recall that as the factor for changing between line voltage and peak voltage. So in this case, our PIV would need to be 170 volts. Now, another important value that we need to look at is the peak to peak voltage. Now, what you have to be aware of, most people think of peak to peak voltage in terms of an AC waveform. And if we looked over here, we would say 170 is the peak here to 170 here. So on the AC side, the peak-to-peak voltage here is actually 340 volts. Now, in fact, the definition of peak-to-peak voltage is the voltage from the most positive point to the most negative point in a waveform. And so we can apply the same peak-to-peak voltage analogy here. And what is our peak-to-peak voltage on the load? Well, the highest point is 170 volts. The lowest point is right here at 0 volts. And so our peak-to-peak voltage is in fact 170 volts. Or we could say for a half-wave rectifier, our peak-to-peak or ripple voltage is equal to E peak. So peak-to-peak voltage, 170 volts, or simply E peak for this rectifier. Now, when it comes to the single-phase half-wave rectifier, the load power is a little bit of a different thing to calculate, and I'm going to explain that just shortly. Okay, now when it comes to calculating power, I want to show you something interesting. It's not real intuitive, and so when you look at this rectifier circuit, there's two ways that you might think about doing this. Now we know that according to Ohm's law, power is just E times I. So if you were to take 54 volts, E of the load, times 7.2 amps, which is I of the load, multiply them together, you got 388.8 watts. And at first glance, you would think to yourself, well, why wouldn't that work? But it's something interesting that actually happens. When we do power calculations with a single phase rectifier, what we really need to think about is the size of the waveforms that are involved, and we actually need to look at it from the AC side, because really what's happening is the line voltage that you apply, the current that flows, and the power that develops is really best determined by the line voltage. And the reason that we divide by 2, we take the line voltage squared divided by the resistance, and then we divide by 2. In this formula, why do we divide by 2? Well, the reason is that if we had a rectifier, and let me show you the waveform for the whole cycle. If we had a full waveform like this with two power humps in there, then we wouldn't divide by 2. But seeing as it's just one that's in there, what we're really looking at is this is really just what we could call half time. This is a half time rectifier. So we use the line voltage, the load resistance, and then we divide by 2. And so we take 120 squared divided by 7.5 ohms. We divide that by 2, and we arrive to 960 watts. Now that's almost 3 times as much power as you would have calculated using the DC values. So please just be aware. I'm going to just show you that this is not where we want to go with this. Okay, so for future reference, don't do it that way. Make sure you use the line values and the resistance, and when it's a half-wave rectifier, divide by 2 because it's only half time. All right, now we're going to take a look at the full wave bridge rectifier. Now this is also a single phase rectifier. The facts, quick facts on this. First of all, the number of diodes required are 4. Here's what the circuit looks like. You have your line 1 to neutral. You essentially come out, you place an anode to one line, and then basically inverse connect. So the two cathodes of these two diodes connect together, and the anode goes to the line on the other side. Now at the other end, you just reverse that. Here you had an anode and an anode connected to the line. Here you put a cathode and a cathode connected to the line, and the two anodes are connected. Now your load, your DC load, fits between these two center points between the diodes. And there are many different ways to draw them, but this is a fairly straightforward way of looking at it. Now, look at the AC waveforms. As we apply here, we're going to see our AC waveform, and look at the DC output. Okay, this is our output. This is our input. AC in, DC out. Now we have 2 ripples per cycle. Okay, our form factor in a half-wave rectifier was 0.45. This one is going to give us exactly double the voltage. So we can take a look. This is going to be 0.9. E line times 0.9 will be the form factor. That means that if we were to have a 120 volt supply here, that would actually give us 108 volts would be our average voltage. 108 volts given a 120 volt AC supply. Now, what about the PIV of the diodes? Well, each one of these diodes has to be able to block the full line-to-line voltage, and so the PIV in this case would equal 170 volts, or we could just say E peak. Now, the ripples. Here we have a 60 hertz supply. Every time we get one cycle, we get 2 ripples. That gives us a ripple frequency of 120 hertz, or it's the supply frequency times 2. What about our peak-to-peak voltage? Well, on our output side, peak-to-peak looks to me like the peak is 170, given our 120 volt line voltage. 170 volts would be the highest, most positive voltage. 0 will be the most negative because we start at 0, we arrive at 0 halfway through the cycle, and we finish at 0 again. And so that means that our peak-to-peak voltage is literally our peak voltage. So in this case, 170 volts. Now, we're going to go ahead. I'm going to write a few numbers on here, and we're going to look at the diode current, and we're going to look at the power of the load. All right, in this example, I'm going to use 10.9 ohms. And what I'm actually looking at then, we just need to take a look with our voltage of 108 volts, 108 volts, which is E line times 0.9, this being 120 volts. And 108 divided by 10.9 is going to give us some current. Now that looks to me like it's going to be 9.9 amps. Now something interesting happens. Does that full 9.9 amps have to go through each of the diodes? And this is the way I would look at it. In our positive alternation, we would actually have current that would come this way through the load, and then this way through this diode. So it would follow like this. When we switch, what would happen is that the current would then come up through this diode, same direction through the load, and this way to the other line. So we really have 2 diodes in series at any point in time. So in fact, what happens is the diode only has to pass current 50% of the time. And so when we calculate diode rating for current, what we do is we go I load divided by 2. So in this case, we would be looking at 4.95 amps. 4.95 amps would be the rated diode current in this case. Now let's take a look at the power. We already took a look at why we need to use line values. So I'm simply going to say that in this case, we're going to use 120 volts squared divided by 10.9. And we're going to divide all of that by 2. Okay, so 120 squared, 10.9, 1,321 watts. Now, do we need to divide by 2? Here's the question. Well, this is a full wave, so in fact, guess what? We don't actually have to divide because this is a full wave rectifier. In other words, we have power in both alternations, so it's literally just going to be the 120.2 squared divided by 10.9. No dividing by 2 necessary, and this one equals 1,321 watts. And there's your load power for this full wave single phase bridge rectifier. Okay, the next rectifier, this is the final of the single phase rectifiers, and this is the full wave bridge, the full wave center tap rectifier, center tap. And so let me just show you how this works out. Where does the center tap come from? This one is done using a transformer. So as you can see, we're going to have a primary winding of a single phase transformer, in this case 480 volts. This is a 2-to-1 transformer, which means that my full secondary will be 240 volts, from end to end. Now the center tap is where we are actually going to connect our load. And so in this case, I want to make sure that you understand the line voltage. When we talk about E line for this particular rectifier is the voltage from one end to the center tap. And so it's really, if you look closely, E line here is equal to 120 volts. The full secondary voltage, of course, is 240, but we're only using 120 of it during one alternation, and then we're using 120 on the other side for the second alternation. This gives us a full wave output, which looks like this, of course. Here's our AC input, and here's our DC out, which is 2 ripples. So this also gives us a full wave output. And so many things are actually going to be the same in this. The form factor still 0.9 like the previous full wave was. Now, if this was a 120 volt line voltage, we could move right along and we could say, well, what's our average voltage going to be? It's going to be 108 volts. Now, in order to take a look at the amount of current per diode, we would need to have a resistance value. So I think I'm going to give that to you right now. That's going to look like 4.75 ohms. 4.75 ohms. And so what we have is 4.75 ohms, 120 volt line voltage, 108 is our average voltage right here across the load, 108 volts. And so that will give us a current of about 22.74 amps. 22.74 amps. And because that current is flowing through this diode half the time, and then through this diode half the time, in fact, the current that the diode has to be able to handle is just half of this, which in this case is about 11.37 amps. Okay, now the PIV, let's take a look at the PIV for this diode. A little bit different for this one. This is its unique characteristic, I guess we could say. If you take a look, while this diode here is conducting, this one has to block. But what it actually has to block is, if you look, this is the voltage that's being expressed across the load. But this diode has to block all the way from this point, the full secondary voltage across there has to block while this load is conducting. So that means that in fact, our peak to peak voltage in this case will only be 170 volts, which is 120 times root 2. So it's a peak of 120. But interestingly enough, when we come to our peak to peak voltage, let me just write this down first, 170 volts. When we come to our PIV, it actually has to be 240 times root 2. And so that's going to actually equal 340 volts. So the PIV in this case, 340 volts, or the peak of 240. Now, what about our ripple frequency? Still, this one is going to be 120 hertz because it's literally two ripples per cycle. And in the end, what we want to look at is we're going to calculate power here in the same way that we did with the full wave. And we're simply going to take and we're going to use 120 squared divided by 4.75 ohms. No need to divide by 2 because we are talking about a full wave rectifier. And the total power winds up being just over 3 kilowatts. And so there you have the 3 examples of the single phase rectifiers. We started with the half wave, and now we have 2 full wave rectifiers. First the bridge, and now the center tap. So that pretty well represents the 3 single phase rectifiers. Okay, so now we've taken a look at the single phase rectifiers. What we're moving on towards next is going to be the 3-phase. We'll be looking at those, and so you'll be able to rely a little bit now back onto your 3-phase theory, and we'll see that the 3-phase rectifier is actually quite a bit more efficient, puts out a lot more power for a given voltage, and so that will be coming up next.